So, tonight's speaker is Taylor Patti, a senior research scientist at NVIDIA. Her research interests are all things at the intersection of quantum and classical computation, including quantum algorithms, machine learning for quantum applications, and the efficient simulation of quantum systems. She holds bachelor's degrees from Chapman University in Physics and Computational Science, Mathematics, and Spanish, as well as a master's and PhD in theoretical physics from Harvard University. And without further ado, let me welcome up Taylor Patti.
All right, well, thank you guys, everyone, so much for the lovely introduction and for having me out tonight. I've been really looking forward to it because, believe it or not, despite the fact that I'm a theoretical physicist, my favorite people to talk with and to work with are actually computer scientists. And, that's probably why I work at NVIDIA, but I think it's really well-rooted in some scientific realities right now. And that is that so many of the most interesting and useful problems in quantum mechanics, like material design, designing new materials, drug design through quantum chemistry, finally solving that pesky nitrogen fixation problem. So many of these problems, we can write down on a piece of paper the solution right now. I can code you up a Python script that could solve it in theory. But the issue that I have is that it scales exponentially, it's too darn big, and I can't even begin to solve it. So that's where I have to work with you folks. That's where I have to work with computer scientists and engineers. I have to work with engineers to maybe make a quantum computer that can solve it. Or I have to work with computer scientists to do a truly heroic HPC run as large as I can. Maybe I have to work with algorithms people to get an approximation algorithm that can kind of approximate this quantum system as best as we can. Or I have to train an AI model that can predict what it would do or how to correct it. So I really need computation. I really need ACM type folks, right, to work with to really advance quantum science. And so I'm going to talk about a lot of that today, what I do, HPC and AI for quantum. But before I get to that, I'm going to make everyone suffer here a little bit with the fundamentals of quantum mechanics. And there's a reason for that, and that's because it's good to appreciate how cool and exciting quantum computing is, right? But to really appreciate why it's useful, you have to appreciate why it's hard. Why it's hard and why it's useful are two sides of the same coin. And so we're actually going to spend the bulk of the time kind of introducing that. All right, so let's jump right in then on these fundamentals. And I actually want to start with the history of this stuff. And usually I don't like starting with the history because it's boring. But in quantum mechanics, it's actually kind of fun and it's super relevant and quick. So I'm going to do a very abbreviated history. I'm going to start in about 1900, but I could easily start in 1800. But we'll start with when things really got moving quick. And I'm going to start with a physicist named Max Planck. And so Max Planck wanted to understand why our predictions about how hot objects like hot pieces of metal radiated energy weren't right. In fact, they were so not right that we called it the ultraviolet catastrophe because they predicted that basically a warm piece of metal from across the room would give you a sunburn so bad it would, like destroy your arm, basically. It totally diverged when you got to faster frequencies of light. So we knew it was absolutely not correct. So Max Planck wanted to solve this but had no idea how. So this crazy man, he took a bunch of experimental data and he sat down without a computer, without a calculator, it's a little bit before 1900, and he fit that stuff by hand. He had no idea how to make it work, but he fit it by hand for months or years or whatever, until he finally came up with two of the most fundamental discoveries of quantum science. Number one, there is a constant of nature. It's called h. We now call it Planck's constant in his honor, which is super tiny, like 10 to the negative 35, and has really weird units like kilograms times meter squared over second squared or something like that. And you cannot do science with small things such as little pieces of light without it. So he discovered this just from fitting the data by hand, being his own calculator. The other thing he discovered is that the way that radiation works, and therefore the way that the world works, only makes sense if you only allow for discrete energy values. So he thought, this is really weird. I think of light as a wave, right? But now I'm finding that it's actually a little packet, a little particle of energy. And so that was really crazy. And that was arguably the start of quantum mechanics. And this inspired a lot of people. One of the people it inspired was a young French physicist named de Broglie. And he said, well, if Planck says that waves are particles, then I guess I'm going to say that particles are waves. So he had no further justification than this. He really did not. Then he took Einstein's equations of relativity and he played with them. And he substituted in, he solved for the wavelength of light, which was very trivial. But then he substituted in what the corresponding terms for a massive particle would be. And then he said, okay, this is the de Broglie wavelength. It's Planck's constant that we just found over momentum. And people thought that this was crazy because it was really kind of poorly motivated, right? But then they did the experiment with, can you guys see my mouse? Good. They did the experiment with electrons, and indeed they found that electrons, a massive particle, was a wave. And then everyone was like, okay, welcome to the 19th century. I guess now waves are particles and particles are waves. I guess that's reality. And so then Schrodinger came along, and he's of course the most famous of all, right? And he said, well, okay, if de Broglie says that matter's a wave, then it better have a wave equation. Water waves, sound waves, all these things have a wave equation. So he did what Planck did. He took the classical wave equation as inspiration, and he took a bunch of experimental data from a hydrogen atom, and he sat there and he fit it by hand without a computer, without a calculator, without anything, until he finally got something that kind of looked like a wave equation, but fit the data. And we call that Schrodinger's equation. Just out of nowhere, he found this. He just worked at it. If you've ever curve fit before with modern technology, you know how hard that this must have been to do by hand. And so finally, this is the three big highlights, I would argue, of quantum mechanics history. But I want to share one more historical point, because it probably answers a lot of the questions that folks in this room are having right now. And that's that if this is how the world works, then why don't I see these quantum effects? And the answer that Niels Bohr gave, and really made quantitative as well, is what we call the correspondence principle. And it's that you don't see quantum mechanics around you because Planck's constant is tiny and you are big. You are so, so very big compared to Planck's constant. When things are about the size of Planck's constant, 10 to the negative 35-ish, you'll see it. But when they're not, you won't. So this is not only big in terms of length, this is also big in terms of, say, energy. If something is high energy, it becomes non-quantum looking. So to give you an example, let's take a baseball that I throw. It's a small object, I'm not an athlete, it's gonna have low momentum, right? It's gonna have very low momentum, and even so, the de Broglie wavelength of this thing is gonna be 10 to the negative 35. That is so, 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 so tiny, you will never see it. Our best electron microscopes are about 10 to the negative 12. So just to give you a view of why it totally is consistent, that small things be weird, but we never see them. And so and small things are weird, small things are very weird. And so I wanna just take a couple minutes here and I wanna give a super high level understanding of the postulates of quantum mechanics. These are all things that crazy physicists like Planck and Schrodinger basically guessed and checked, but they checked them and they're extremely accurate, so don't worry about it. They're true, I promise you they're true. They're some of the most exactly studied laws of nature. But don't worry if these are a little strange. We're not gonna ignore the math to the side. That's for the mathematically inclined. We're just gonna go over the concepts here. So the first postulate of quantum mechanics, so after these 5 things, you know everything you need to know about quantum mechanics. The rest is derivation. The first postulate is that you can fully specify any quantum system with what we call the wave function, or you could also call it as quantum state. So this is what you solve for in Schrodinger's equation. Remember this equation down here? That's what you're solving for. That's what we're always going after because it tells us what the system does. When you measure a quantum system, you actually don't measure the wave function. In fact, it's very possible that the wave function doesn't exist anywhere, that it might just be an ontological tool that we use to do math. But what you do measure is you measure the absolute value squared of that wave function. You actually get it as a probability distribution. You draw a sample from it. That's how quantum mechanics allows us to know anything about it. It restricts it to that. Postulate number 2 is just saying, hey, don't worry about the fact that your wave equation is this weird, complex thing, because whenever you measure anything with quantum mechanics, you're going to get a real value, which is good, because we can't measure imaginary things. Mathematically, this means it's going to be a Hermitian matrix, and I already said that in quantum mechanics we represent states as vectors, right? Oh, thank you. I already said that we represent states as vectors. Well, we represent things that you measure, observables, we call them as matrices, and they have to be Hermitian so that they always have a real value, so that you always get that. Postulates number 3 and 4 say that basically in quantum mechanics you only ever measure very certain values, no matter what state you're in. If you're in a special kind of state, you'll always measure the same value. We call this an eigenstate. So for instance, if this is what you're measuring here, this matrix, remember matrices are how we measure things, it has 2 eigenvalues for the mathematically inclined, right? 1 and -1. You're always going to measure 1 or -1, just like Planck could only have certain values of energy. If you're in a special state that's an eigenstate, you'll always measure that eigenstate, so 1. But if you're in a mixture of these eigenstates, you will measure a mixture of these 2 values that will they can come out to some average value, some expectation value that is not 1, but you will only ever get 1. So for instance, of this state, the expectation value is 0 because it's 1 minus 1, but you'll get a ton of +1s and a ton of -1s and they'll average out to be 0. And the postulate number 5 is that Schrodinger's equation is the boss. It runs everything. Everything you want to know about quantum mechanics, you should be able to somehow get from a form of Schrodinger's equation. And so this is what I meant when I said a couple slides ago that it was important to work with computer science folks because everything we need to know about quantum mechanics we can write down, but it's too big to solve. Most of this is Schrodinger's equation. I could write it down, but it's way too big to solve. And so I want to give you guys a little bit of intuition for why it's too big to solve now. So let's talk about this exponential growth of quantum states. If we're talking about 2-level quantum systems, which is what we talk about in quantum computing because we call these quantum bits or qubits, then they're going to grow like 2 to the n. So this is for the rest of this talk. When I talk about quantum things, it's a qubit, because for simplicity and for germaneness, because we're doing quantum computing stuff. So if I just have one qubit, it's quite simple. I have 0, the 0 state, which is a vector, 1, 0. This is just a choice. I could choose a different set of vectors as long as they're linearly independent, but we make this choice because it's very pretty looking. And I also have 1, which is 0, 1. But the thing about quantum mechanics that we've all probably heard here is that we have superposition, right? You're not just one thing. You can be everything at once, any linear combination. So I can be 0 plus 1, or it could be 0 minus 1, or it could be 0 plus I times 1, right? So any linear combination. This makes it a little bit different than classical mechanics, because now I have to represent all answers at once. I can't just have a single bit 0, 1. I have to have a vector, because I always have to make room to be representing the other as well. Now, if I go to 2 qubits, I have to keep making room. So I have 4 different vectors I could have for 2 qubits, right? 0, 0, 0, 1, 1, 0 would be 0, 0, 1, 0. And 1, 1 would be 0, 0, 0, 1. Combinatorics folks are looking at this and being like, yeah, I recognize that. That's my nightmare too. Exponentially large, right? So we have the same situation, but remember, we always have to represent them once. If you work in combinatorics, you can have a solution, and it could be, 0, 1, and you leave it at that, 2 bits. But here you're always going to need 4, because you always need to keep room for the other to track this generally. So when I go to 3 qubits, it's going to be size 8. And when I go to 4 qubits, it's going to be size 16. And you guys already know where this is going to go. This is going to go to a regime where pretty quickly, surprisingly quickly, we cannot compute this. And so this is a big problem. This is, I work at NVIDIA, the world's biggest compute company, right? And this is a problem for me. This is my #1 problem in my research. So you best believe that back in, say, 1981, this was a very big problem for physicists. They did not have the super, even now we can't deal with exponentials, but back then they certainly couldn't. So this problem of it being so expensive to simulate these systems is why, or I can't speculate why, but why I believe that Richard Feynman first proposed the first quantum computer in 1981 at a talk at Caltech. And he basically said, look, guys, we're never going to beat the exponential. I don't care how good your computers are. So we need a quantum computer if we're going to study quantum things. We need a computer that can represent these exponential spaces naturally. And it's kind of like, you can think of it as like an animal model for drugs, right? So if I want to, I can do small simulations like with active sites or something for drugs, and I can kind of get an idea for the drug there. And I can eventually give it to people and hopefully it works. But in between, I need to try something systemic that's not too expensive, like human life. And so quantum computers, you could think of this way. I could do a small simulation with a classical computer, but there might be something bigger, like in bulk, that I can't study until I understand it well, like say a superconductor. Now, I can't just make a superconductor work. It's big, it has all these molecules, all these moving pieces, too many degrees of freedom. But what I can do is program something nice and clean, like some atoms in a vacuum, controlled only by lasers and interacting only with each other. I can make that have a Schrodinger's equation that looks like the Schrodinger's equation of, say, a superconductor. Even if the physics is totally different, it doesn't matter. Schrodinger's equation runs everything. If I can make that Schrodinger's equation look qualitatively like that, I can rescale it and I can make it represent my system. And so this was Feynman's original proposal for the quantum computer. And I think it still is one of the most interesting and advanced ones. I think we're really, really making great strides in studying things like material science, condensed matter physics, so on and so forth, with these sorts of quantum simulators. And I'm really excited to see where this goes. However, when he said this, like anytime anyone says anything, right, he really set off like a bigger fire than he thought. Because people weren't only excited about quantum computers for quantum systems, they were also excited about quantum computers for classical computations. And so this started in the 80s, and really especially the 90s, a rash of what I would call traditional or first wave quantum algorithms. So if everyone knows Shor's algorithm or quantum Fourier transform, all this, that came out of this time. I want to talk about these a little bit, but before I do, I'm going to give you guys a little bit of a disclaimer. These traditional algorithms all require highly coherent quantum computers, highly, highly coherent. We do not have those. So you cannot do these at scale yet. But they're still really interesting ideas, and some people think that one day we will have them. That's the goal, at least. That's the goal we're all working towards. So they're worth taking some time to understand. So I want to show you only one of these in a little bit of depth. It's called Bernstein-Walser-Vrani. And it's not because it's the most exciting. It's not. It's because it's the most simple. And I want to give you guys just the essence of what these traditional quantum algorithms look like. And then if you have that essence, then you can have a better understanding of, say, how something like Shor's algorithm looks like. It's like a little toy model of how these dynamics can actually translate into computation. So Bernstein-Walser-Vrani is a very humble algorithm. It says I'm gonna do a task in one evaluation on a quantum computer that would take me n evaluations for a bit string of length n on a classical computer. The task is this. I give you an oracle. The oracle has some string s that is length n of bits, right? All the oracle will tell you is what s dot x mod 2 is. So basically, if s dot x of some string of bits of your choosing x is even or odd, that's all it's going to say. On a classical computer, you need like a linearly independent set of x's. There's n of those, and then you could solve this problem. So that's n iterations. But on a quantum computer, if you choose to build one, you have the great privilege of doing this in just one shot. So that's kind of the point of this algorithm. I'm going to do this in like at a really high level. I just want the essence for everyone to get the essence here. You start off with this state, this zero state. Remember it? It's 1 and then zeros all the way down. You start off in that state. You put it though into the maximum position state, where all states are equally populated. So you have 1, 1, 1, 1, 1, 1, 1, 1, 1. This is a state that has size 2 to the n. So now you have like 2 to the n different x's in the game. So you're going to be able to evaluate these all in parallel. Quantum computing people hate it when you say that, but in parallel, okay? You now have your quantum version of the oracle. The quantum version of the oracle, it gives you a phase. So if s dot x is even, phase is 0, right? It just times 1. It leaves it the same. If it's odd, it's going to give you a phase of -1. Now, the last step of this algorithm is that you snap that state that's like all populated, all states with some phases. You snap that back into the using these same gates that you kind of blew it up with, right? If you had not put the phases, you'd go right back to that boring 0 state. But because you put the phases, now the right answer is going to constructively interfere with itself. And the wrong answer is going to destructively interfere, like a wave, like the wave patterns you see where the peaks are constructive interference and the naders are destructive interference. And you're going to get exactly one state back, and that is S. And so this kind of logic, hey, I get a superposition for free, an exponentially large one. Let's have it. Okay, put some phases. Okay, now snap it back. Now I have my answer. That is really core to pretty much all of these traditional first wave quantum algorithms. That's pretty much how Shor's algorithm works. But Shor's algorithm, if I were to tell you about it, I would need like 2 pages and a classical subroutine and stuff, right? But Bernstein-Vazirani kind of has this essence, like this core of it, about superposition, phases, and destructive and constructive interference. So maybe let's go there now to Shor's algorithm. That's like the famous one, right? It has an exponential speedup with this, which is absolutely nothing to sneeze at, and it's an algorithm for factoring large integers, which is a very polite way of saying that it's an algorithm for breaking RSA encryption. But as I said, guys, don't worry. Like we don't have a computer that can do this yet, so your bank information is currently safe. That's all good. But this is the idea, is to build something that can do this. So keep that in mind. There's also the quantum Fourier transform. This one's less controversial. It is the Fourier transform that we all know and love, but you can do one that's exponentially large using only a polynomial number of terms. So that's, I think that's a goal we can all get behind. Like that's a very noble cause. And then there's also Grover's algorithm. Grover's algorithm is a little different. It's only a quadratic speedup, but basically it's an unstructured database search. And so you get a quadratic speedup for one simple reason. You basically search your database with Schrodinger's equation, which remember was linear. But then you measure your database like measuring a quantum system, which remember was the absolute value squared. So that's where that quadratic speedup comes from, is from squaring your state. That's the total source of it. So these are the first wave algorithms. But you guys remember I gave you a disclaimer at the beginning, right? Which I said that this is for coherent quantum computers, and we don't have those. So now I have to take a little bit of time, or pretty much the rest of the talk, pretty much the rest of my life actually, and focus on why quantum computers are noisy until I retire, and focus on why quantum computers are noisy. And I just want to take one slide and just talk about quantum noise. And this slide looks like very full. I give this kind of deck to different groups, and so sometimes I give this to people who I want to make suffer with all these equations, but don't worry, we're not suffering with the equations today. We're just going to talk about quantum noise almost like philosophically, right? So the first thing I want to say about quantum noise is I don't think there's too many people who would argue with me when I say that quantum noise is probably the greatest threat to quantum computers. It's really hard. It's what we're always fighting to overcome. I want to do my quantum computation, but it's too noisy. And we call it decohering, that's our term. But basically it turns into all noise before I get a chance to get the right answer out. That's my problem. That's the first thing I want to say about quantum noise. The second thing I want to say about quantum noise is that it's misunderstood. It's actually very cool. Like the mechanism is very cool. It's not like static coming on your radio. It's not like the environment just like ruining your signal, right? It's a little bit more nuanced than that. Quantum noise is your system entangling, many times almost choosing to entangle, almost being the aggressor in entanglement with the outside world. So we've all heard about this resource of quantum entanglement. We know that quantum computers only run because of that. We build these quantum computers that are good entanglers because we need them to respond to us when we try to control them, like by shooting them with lasers. And we need them to entangle with each other because that's the way you do a quantum computation, is by controlling your qubits with one another. And then we act surprised when these pretty good entanglers that we build also entangle with the environment. It's really a double-edged sword. It's very challenging to isolate them from everything but the things that we'd like to control them. And that's the origin of quantum noise. So those are really the two things that you should know about it. It's a real pain. It's a real pain for us, and it's probably our biggest thing to overcome. That's one. And number two, that's actually pretty cool. Like philosophically, it's pretty cool. It's not just some nasty static or something out there in the universe. Okay, so now I've told you that quantum noise is really hard, and I think that this is probably why we have so many different platforms that we've proposed for quantum computers. I'm just going to list a germane few here, because we keep trying to get around it, right? We keep trying to find something that can overcome this noise issue better than the things we have. And we have a lot of great candidates. We have more than are even on this slide, but here's just a few. So our first type of qubit will be the superconducting qubit. So this is, I would say, a very good entangler. So meaning that you can do gates with it quite fast, but it also gets noisy and useless quite fast, right? So you have to have very fast clock cycles here. Superconducting qubits are preferred by Google, IBM, Amazon, Rigetti, a lot of corporate players, as well as always, academic labs. They run on something called a Josephson junction, which is like a fun piece of trivia. It basically lets superconducting current go through or not through. If it goes through, that's like 0 in your bit. If it doesn't go through, that's like 1. That's kind of the mechanism on which they're all based. And right now, I think the company with the most qubits on a chip is 105, but that's always changing. So if anyone has a bigger chip, let me know. Neutral atoms are kind of on the opposite side of the spectrum. These are like the atoms that make up the world around us. They're not connected to any molecules or anything like that. They don't have any extra charges on them. They're just basic, simple atoms. Again, this like trivia point about big words, Rydberg atoms are what are typically used. There's other kinds you could use too, but it's mostly Rydberg atoms if you read that in a journal or something. And yeah, these are really slow entanglers. So they interact with each other slowly, but they decohere slowly. So we have more time to control them, but the absolute number of operations that we can do in a clock, before it decoheres is not too much better. There's about 256 of these on a chip at Quera, and academic labs have some amount fewer, but these tend to be bigger quantum computers at this point, probably because they're so coherent. Trapped ions are a lot like neutral atoms, but never say that to a trapped ion person or a neutral atom person. They'll be very mad at you. But they look quite a bit the same, at least from a high level, right? These are atoms as well. They just have extra electrons or extra protons, so they have a charge on them. IonQ is like enormous now. They're buying up all these quantum startups and acquiring all these people. University of Maryland also has these. There's like 100 of them on a chip at this point, or soon will be, maybe 64 at the moment. These are also really slow entanglers. So they're slow to decohere, a little slower to interact. But something cool about trapped ions is they actually entangle. They have entangling gates that include vibrational modes. So moving together, moving apart. I find that adorable. I don't know. I find that very conceptually satisfying. You don't get a lot of that in quantum mechanics. So I like the motional modes. Just two more kind of germane platforms for you guys. One will be vacancy centers. So these are primarily had by academic labs for quantum computation, but for quantum sensing, they reach quite further. So vacancy centers are, you take a diamond, you remove a carbon, which has 4 valence electrons, and you instead put in a nitrogen or a silicon. This has 5 valence electrons. So now you have 2 free pairs of electrons. This is optically active. You can do quantum information, quantum computing type stuff with that. And that's how they make these. So they're not very scalable. So there's not a lot of people using them for quantum computing, but they retain a lot of interest as quantum sensors. And I really like the topic of quantum sensing because it's kind of like the opposite of quantum computing. In quantum computing, we're always like, oh, the environment is making my qubits noisy. How terrible. In quantum sensing, that's the whole idea. Like you want your qubit to be sensitive to the environment because that makes it a good sensor. That makes it a highly sensitive sensor. So I'm really all aboard. I don't work in quantum sensing, but I'm jealous of those who do because I feel like it makes sense. And then finally, last but certainly not least, especially not anymore, is optical quantum computing. These are companies like PsiQuantum, which is a big name right now, and Xanadu. These are all done with photons. These are totally different than the rest of these platforms. They have kind of a whole different business model, if you will. It's measurement-based, it's probabilistic. It's actually the only platform on here and one of the only platforms in quantum computing that I don't or haven't worked with. So this to me is something that's, I'm a neophyte here. I don't know much about it. I couldn't answer too many questions on it. Everything else, yeah, I've been there. But optical quantum computing, that's a horse of a different color. But it's gotten a lot of interest lately, and I think we'll see something interesting happen. I don't know what it's going to be, but we'll see something interesting happen there. Okay, so this was a crash course on all the things that made quantum computing, well, let's say all the quantum mechanics that made quantum computing not only useful, but hard, and therefore useful, right? And we went over the systems that it's on and our big problem with noise and all that. And so for the rest of this talk, I just want to take some time and talk about my research areas at NVIDIA. So this is where we get to that HPC and AI kind of stuff. And when I first came to NVIDIA, I worked mostly, these are my research topics right here. But when I first came to NVIDIA, I worked mostly on quantum algorithms. And I mostly don't work on quantum algorithms anymore. But it's no insult to quantum algorithms. It's just that I'm a very impatient person. And so when I was finding that these quantum computers just weren't ready yet, I didn't want to keep making algorithms for them, right? For quantum computers that don't exist yet. I instead wanted to help make those quantum computers. So I've since shifted most of my effort, still theoretical, not experimental, theoretical, computational, but still into supporting a quantum architecture and hardware development. And this has kind of two main strategies that I take. The first would be approximations and high-performance computing for efficient simulations of quantum systems. So quantum systems are hard to simulate, but what is the best I can do by exhausting myself, like both mathematically and exhausting NVIDIA GPUs, to be able to probe the most interesting and large systems that I can, as well as AI for quantum systems. So what models can I train to be able to tell me what a quantum system is going to do, or what model can I train to help me correct a quantum system so that it might behave better in the future? Everything here. So for the next few minutes and the rest of this talk, I'm gonna go through some projects, some of them ongoing, some of them recently finished, and we're just gonna like speed date some of my research. And just like speed dating, like maybe some of them will be interesting and some of them won't, but either way, like we'll just go through them all. So I wanna start off maybe where we left off with noise, right? We already said that noise is a big problem. We physicists have just basically accepted right now that we're never going to mitigate noise enough to just leave it alone. We've accepted that we're going to need some error correction. Noise is going to happen. We're going to need to correct the errors that it causes. And so we're going to have to take a page from the book of classical computing and classical information processing and have some error correction. And so this first project I want to talk about is about training an AI model to correct these errors, or more in particular, to recognize the errors that we see from the measurements that we take and tell us how to fix them. So basically how it works is you take your qubits and they might have some errors on them. Like this one has a bit flip error right here. And I'm going to take some measurements of my state that don't destroy it. They don't destroy my information, but they do tell me what's going on with it. They do point to potential areas where I have some errors. The issue I have though is that these weird measurements are pretty inscrutable. With any kind of a large quantum system, like it's very hard for a human to look at that and tell you what's going on. It's not apparent. So here's where an AI model comes in. I'm going to train my AI decoder to look at these weird measurements and to tell me, oh, yeah, there is an error. It's here. And if it's correct, then when I try to correct that error, I'll get a clean quantum system. And if it's incorrect, when I try to correct that error, I'm going to make it worse. So it has to be correct. And this is the idea of an AI-based quantum error decoder. And so this is the work that we're actively doing, and we're really excited about it. Because it's not just work that would be required for developing quantum computers, it would be work that's required for maintaining them. Even if we've accepted that we're never going to have a noiseless quantum computer, we're going to have to fix it. So I would need only ever bigger and better AI decoders. I would never not need them anymore. And so during this is work in progress, because we got sidetracked doing this work. We had a problem. We didn't have enough data. We wanted to model noisy quantum systems, and it turns out that noisier quantum systems are actually way harder to model than even clean quantum systems, like ideal quantum systems. Because what you need to do is you need to sample a lot of different potential errors and then build that state every time. So remember the states I want to build, they scale like 2 to the n. They require an enormous amount of computation. But now I need to build different states where I'm kind of substituting in different errors. And this becomes a huge computational problem. And so in order to train that decoder, we had to take a side quest. This is some work I did with colleagues at NVIDIA. This will be at supercomputing. So if anyone else is ACM is an ACM thing and an IEEE thing, so maybe I'll see some of you guys there at Supercomputing in November. Come say hi. What we did is we kind of designed an algorithm that did two things. First of all, it let us sample the most important errors so that we could compute as little as possible. We wanted to compute as little as possible to teach our decoder. And second of all, we designed an algorithm that systematically stored as many intermediates of computation as possible. And this way I don't have to redo work. And this increased the amount of data that we could sample by about 1 million times. Because we were able to recache those intermediates and keep using them, keep using them, keep using them, keep getting data for our decoder. We know that AI models are super data hungry, so this had to be done. And we were able to, with just like a couple thousand hours of GPU time, get about 1 trillion shots from an extremely large quantum state vector that most computers in the world can't even build, like let alone process. So this is like an extremely efficient method. And so these are the kind of efforts that are, maybe this in tandem of these two pieces of research are a good representative. I want to train an AI model. That's an ML problem. That's definitely a GPU problem. That's definitely an NVIDIA problem, right? But it's also an approximation problem, and it's also an HPC problem. And so when you get all those elements together, then you could start to kind of peel back the code and try to start learning a little bit more about quantum systems and how to help us develop quantum computers. So this has been like AI, right? AI for helping to correct a quantum computer. But what if I'm really frustrated with quantum computers in general and I don't really want to build one anymore? Or just in the meantime, right? Maybe I'll say in the meantime. In the meantime, I don't want to build a quantum computer, but I do want to use AI to do things in quantum that I couldn't do before. And so that's what this next idea is about. It's called neural quantum states. And these have been around in some form for about 10 years, but now we're working on them more intensely. So what neural quantum states is the idea that when I have a system that has a lot of structure, for instance, I have like a condensed matter problem that might help me learn about new material design, or I have a quantum chemistry problem that might help me learn about drug design. You always hear like material design and drug design a lot because these are two of our greatest hopes with quantum computers, right? Well, these are definitely going to be big problems. They're definitely going to be huge problems. I'm going to need to represent these states by many, many, many floating point numbers. Maybe I'll need millions, maybe I'll need billions, but I might not need 2 to the n. These are natural problems. They probably have some structure. They probably have some symmetry. I might not need to fully exasperate my worst case scenario and need 2 to the n different floating points to represent these. So the idea here is to have a deep neural network instead be my state, and it might have 1 million parameters, it might have 1 billion, but it won't have 2 to the n. 2 to the n is just particularly nasty. That is the one thing I cannot abide. And if you have a state that has enough structure, and if you have a state that has enough symmetry, then you can actually get a deep neural network with many fewer parameters to approximate this state. So now you can study your condensed matter physics, now you can study your quantum chemistry in this more compact way, because you're letting the deep neural network learn whatever the structure is, learn whatever the symmetry is. You don't care, you don't know, it's data driven, but it's highly compact. So this is work, as I said, that's been going on for like 10 years or so. But I'm really pushing NVIDIA to get involved. We have a great collaborator who's been in the space a long time, Juan Carrasquilla at ETH Zurich. And I really want to couple his physical know-how, right, his group's physical know-how and intuition for these systems with like giant GPUs and AI experts. I mean, I really think that we need to, again, the whole thing about being friends with computer scientists, this is a project that really embodies that. This is a project where this is really super necessary. And working on this project, this neural quantum states project, got us really excited about another possibility, and that is neural quantum operators. So this is work that we do. In particular, this is a Fourier neural operator, which was pioneered by the Anand Kumar group at Caltech, who are our super close collaborators. We love working with them, and we've had several great projects with them. And so a neural operator, for folks who are not familiar, is a lot like a neural network, except for a neural network is always learning like a fixed input size, a fixed output size, and it's learning a function. But a neural operator is learning a class of functions for a variable input size and a variable output size. So it's, in many ways, it's like a generalization of a neural network. So the Fourier neural operator is a neural operator, but it uses what we call Fourier layers, which is just a fancy term for if you have a Fourier transform, the same Fourier transform, again, as I said, we all know and love, like all physics and math and engineering uses this, but it's parameterized with learned parameters. So it kind of can capture that structure. It can take advantage of that structure very efficiently because it's, or I should say it should take advantage of the structure of differential equations very efficiently because that's what Fourier transforms are kind of made to solve. And so it really takes advantage of that by having this as part of its structure. So normally what you would do with a neural operator would be something, engineering-wise, right? So here is like turbulent flow, probably from an airplane wing or something. I know they help build airplanes. I'm not an expert in airplanes. But you give it some initial conditions, and you calculate the ground truth through really computationally heavy computations, right, with some sort of performant computing platform. And then you train the neural operator to make these predictions. And eventually it's making predictions that are as good as these really heavy computations. But the neural operator can do this much, much, much faster. And because it can do it so much faster, and sometimes it can do it differentiably, you could then choose it to do, you could then train it to do nice things like inverse design. So this is the whole idea here. And so we took this technology and we applied it to Schrodinger's equation, basically. So now instead of our input being some initial turbulent flow, our input some initial state, and instead of our output being some output flow or whatever kind of physical quantity of classical interest, right? We now have a quantum state as our output, a quantum state that's undergone Schrodinger's equation. And so we were able to train this very well. This work recently finished. And the results are really cool, not only because it's so much faster than doing the traditional integration. The results are also really cool because you could train it instead of with data that's coming from a classical simulation, right? You can instead train it with a quantum computer that is so big that one of these quantum simulators I talked about earlier, that no classical computer could touch it, right? So I could actually train it with a physical system instead. Now the physical system, though, we know is limited by coherence, right? We know it's limited by noise. So I might only be able to train it from time 0 to time t. But what the Fourier neural operator can do is learn 0 to t, but it's also reapplyable. So I could reapply it and get to time 2t, get to time 3t, get to time 100t, whereas with a physical system I can't. So this is a great way, the idea here, the hypothesis, is to reapply this many times to extend not only to accelerate how quickly we can study these systems, but also to study them for much longer times and at much later scales than we could have with either a classical computation or a physical experiment or physical quantum computer a la Feynman alone. So that's this idea. And this idea about FNOs for quantum systems works so well that we decided to try to build qubits with it. And so these final 2 slides of mine are going to be about 2 different projects that are all about using these FNO models of AI models to design qubits. And both of these systems are platforms that I did not list on my most popular qubit page. And that's because these are systems that are not as well solicited. Okay, that might be, people might disagree. They might think that their system is very well solicited. I don't know. But let's put it this way. They are 2 systems that are held up to be very hard to design. Very counterintuitive for a human being, even a grad student who lives and breathes with it all day, to design. And so that's why we chose these systems, because they're held up to be so hard to design that we said, okay, aha, this is where AI can make a difference. This is where there's a human element. The human element alone can make good design choices. So the first project I'll talk about is with our friends at the Neurong Lab of UCLA. And so they want to build a quantum computer, or they want to help their friends build a quantum computer with molecules. And so molecules are really great. They have a lot of potential for quantum information because they have so many degrees of freedom. They have all these optical excitations just like atoms, right? But they have more of them because they have more atoms. And then they have these motional degrees of freedom as well. They have oscillations and rotations and all these sorts of things. So that's a lot of potential, right? That's a lot of complexity that I can harness. However, it's also a lot of intricacy that I don't really know how to handle. Right? It's very counterintuitive to design pulse sequences for these. So we trained an FNO to do so. And it did so really well with extremely high precision. And working with these FNOs, as I said, it did so much, much faster than regular simulations that you could do of the base physics, right? So it's about 1 million to 1 billion times faster than what you could do if you just sat there and integrated your equations of motion like Schrodinger taught you to, right? And because we have this huge speed up, we're now training it to do inverse design. And our hope is that with inverse design, I'll be able to say, oh, I want the following thing to happen to my molecule. I want the following quantum computation to happen with my molecule. And then the FNO would be able to do inverse design, or some supervisor AI model using the FNO would be able to do inverse design and say, oh, then you need these sequence of lasers. You need these frequencies of lasers, these intensities of lasers. You need this control sequence. And so that's the idea here, is that it's hard to know what exactly you need to do in terms of controlling your system to get the output you want. Train one of these models so that you can tell it what you want, and it can tell you what sort of control sequence you need to put into it. And that's the same idea, but on a very different platform with this final slide of research here. This is for quantum dots, is what you call these sorts of quantum of qubits. They are cut straight into semiconducting material, like a lot of different electronics are these days and have been for some time. And this is a collaboration with our friends at Oxford and the ARES group. And so they build these quantum dots and they have to kind of do this terrible simulation in order to design just one quantum dot, right? They have this binary image of what they call gates. This is basically cuts that they would do in their semiconducting material. And then they have to do all these transformations and physics approximations to finally get to this figure, which is the hole density, which is a fancy way of saying that this is the interesting physics going on right here. So here's actually their qubits. The issue, though, is going from here, this binary image, to here, this physics that happened after many different transformations and simulations is super counterintuitive. It produces all the time very suboptimal designs, and it's really hard to scale. So this is for 2 qubits, and it's hard enough to do. But if you want to do, hundreds of qubits, as we all aspire to do one day, right? It just becomes intractable. It's not intuitive. Humans cannot look forward and say, oh yeah, I need to make my cuts in a semiconductor look like this in order to get qubits like that. There are very few designs that people build intuition for, and they're certainly not big ones. And so what we're doing is training an FNO to go from here to here. It's a Fourier neural operator, so it knows all about differential equations. It knows all about Maxwell's equations. It can learn the structure of going from here to here. And it's done exceptionally well. It's many orders of magnitude faster, and it's opening up whole new areas for us to explore in terms of inverse design. So right now we're doing that same process, right, where we train some sort of a supervisor model such that instead of going from here, starting here and having to guess and check over here after very time-consuming calculations, I can now say, oh, I want a qubit that looks like this. Give me a set of qubits, give me a quantum chip that looks like this, and it can tell me the mask I need to use. It can tell me the way I need to cut my silicon. And so this is another area where AI can help us hopefully push forward and get better quantum computers. And with that, if you folks have any questions, thank you so much for listening.
For your error correction first project, is it for superconductors, like you use surface codes or LDPC, and what kind of noise models did you use?
It's an LDPC code, and so we're using both Clifford and non-Clifford noise models, and right now we're trying to keep it as kind of generic as possible. We're really trying to stretch the limits of genericity, but I'll let you know when we're finally done with it how well we were able to do on that. It might be that we need to resort back to some very particular noise model to get enough signal.
So just, okay, and then one anecdotal question. Jensen Huang earlier said quantum computing has a long way to go, and about a month later in his presentation, which many of us watched, he switched on that. What happened?
I've been at NVIDIA about 4 years now, and I always say the following thing, and it's very true. I'm a religious woman, and so I know that it's a sin to try to guess about divine will. I cannot tell you why good things happen to bad people, and I cannot look into the mind of Jensen. But I know that he's a great CEO, and he's never steered me wrong. So that's all I could say.
On that thing you had where you're doing QFT and back, that one. So with the real quantum computer, you'll never be able to do the low digits, like the least significant bits, because the precision would be insanely high because of the crazy frequency divisions. So do you cut off all those low bits when this happens and in your other QFT type simulations?
Yeah, so actually, that's a good question. Actually, this is a classical Fourier transform. So this is just like the model on a classical chip, and it's learning with a Fourier transform. But you are right that we do see us dropping modes, and we drop these modes to just keep those most significant nodes. But this is a classical Fourier transform.
Okay, second question. You gave a pretty exhaustive list over the course of the presentation on all the different kinds of qubits. Is your mission of topological because it hasn't shipped or because it will never ship?
Oh, no, I couldn't say. Now, I really don't know what the future brings, but my personal mission is to advance, as so dictated to me by Jensen Huang. So dictated to me by my manager, as I understand it, is to basically advance science in the way that I'm trained. So I'm a physicist, right? I'm a quantum computing person. Is to advance science in how I see fit, and I think that this is by working on all the different systems. It's kind of like a cat race, right? You ever race cats?
Yes.
Yeah. So they don't run where you want them to run. You know what I mean? Like one will come out of nowhere and be like, it'll win, and it was all the way in the back of the pack. So I don't know. I just work on any system that's relevant to me, but my job is to advance quantum science, which I believe is by helping build these architectures from a theoretical and computational perspective, and to do so using GPUs. I want to use GPUs because they're a great tool, and I want to do things that people couldn't do without GPUs. Because there's a lot of great researchers out there who do things without GPUs, right? But it's my job to do it with. And so I look for problems that have that structure, which is the vast majority of problems in quantum computing, honestly.
If I can have a third question. Is the focus of NVIDIA on simulation and expanding that, or is there a way that it participates heavily once quantum computers are more of a reality?
Yeah, again, that comes back to that divine will question. I couldn't say. I just kind of plug along with my research, right? Honestly, I have a very academic position there, right? I just work on advancing the science. In terms of NVIDIA's long-term strategy or beliefs, I honestly couldn't speak to that. I think it's probably strategic on their part because they know that I like to talk and I like to drink and I like to talk. So they probably wouldn't tell me the secrets, you know? They're just going to keep me doing my little research thing because they know I'd leak it. So I honestly don't know.
Okay. All right, thanks.
Hi, thanks for great talk. I have two questions. One deals with the energy. What are the differences in energy use between among various methods?
Oh, the difference of energy,
How much
the actual computer that you're burning.
Right, basically, which is more expensive in terms of energy?
Yeah, this is a great question. Because there's a lot of people, in quantum computing, I had it on some of the slides, but I didn't explicitly say it. There's this concept of quantum advantage. Like, what can I do with a quantum computer that I can't do with a classical computer? And some people say it'll be faster, and some people say it'll be bigger, but some people say it'll just be lower energy, like you're alluding to, sir. And so that may be the case in some cases. Now, you do have to fight the overhead. So let's say I had some superconducting qubits, and they were a great quantum computer. Well, I have to keep them in a fridge at millikelvin, so that burns a lot of energy. So I'd have to be saving enough energy with my computations to make up for that fridge. But then after that, it would be all gravy. So there's so many different platforms, but that is probably my favorite form of quantum advantage, if for no other reason than it's mentioned very seldomly.
Okay, and the other question has to do with how the process of determining whether you are getting correct answer or incorrect answer. You had it on a slide a moment ago. And here the question is, are you just getting yes, no answer, or do you also get additional information?
Okay, so how would there's two answers to this question. The first is, how would I know at test time? I would know what I was preparing, and I would know what I would expect out. So that's how I would test this. How would I know in real life? I would not. And so it better work. You better make something robust that for general things works, or you're going to get noise out. Garbage in, garbage out.
So basically you get yes, no answer, but no additional information in terms of degree, for example, of correctness. Am I getting close, or did I hit it directly?
You definitely could, though. I see what you mean. Are there backups I could put in? I always could. I could have a greater code distance. And if I had a greater code distance, I could allow for more errors. I could do a repeat round. I could do a repeat round and say, oh, yeah, actually, I must have 2 errors because I have a code distance great enough that I could have 2 errors and still catch it. Because before I was getting 1 error, but now I'm getting 2. I must have messed up. And maybe, these are very probabilistic at times too, maybe on the second round I'll catch it.
So question, do you envision quantum, so qubits to be general purpose, like we're buying a CPU, we can do everything? Or do you, with your last example, you're designing a qubit on the fly pretty much, so that you have different qubits for different applications? So what's your vision?
That's a really good
Personal
question.
opinion.
Yeah, I would say that if we're going to try to do these first wave algorithms, we might have multiple different kinds of qubits, just like you do multiple different materials for your CPUs and stuff, or I have a solid state drive and I don't, and all that kind of stuff, right? But really you would be fine for these first wave algorithms. Let me flip back to them. You'd be fine to do it on any platform as long as it was big enough, coherent enough, so on and so forth. However, there might be a situation where you have a quantum simulator like this that's emulating native quantum systems, right? But it's emulating them. It's not that system. You might need more than one of these because maybe they couldn't do some certain interaction. So like off the top of my head, for instance, I know what I've done with neutral atoms before. The system I worked with, it wasn't Rydberg. We could do an eye swap. And then with Rydberg, you can do a control knot. Now you can always map eye swap into control knot as long as you have single qubit rotations because that's a universal set of quantum computing for quantum computing. But do I actually want to do that? Probably not, because that's going to be many more different operations. So depending on how flexible this platform is for actually simulating other quantum systems, it may be beneficial to have more than one modality.
I came into this knowing pretty much nothing about quantum, and I feel like I know even less now.
Me too.
Maybe that's just the quantum algorithm in my head working. But I also work in cybersecurity, and this, quantum is like the next Y2K in terms of encryption. Where do I learn more, or how do I learn more? Is it like an audiobook I could just download?
Yeah, if I were you and I worked in cybersecurity, I think what I'd be, well, first of all, I would take a deep breath and go look at some of the coherence times of these qubits. But second of all, you could actually look at what we call post-quantum cryptography. And so there's a bunch of people working on things that cannot be broken by Shors or anything similar to Shors. And I would say they have a head start on us. So I think that they're going to be there and be upgrading systems before we ever catch up to them and start like stealing people's bank account information. So that's where I would start, would be post-quantum cryptography. And it's also like very strong cryptography in general. There's nothing wrong with it. You might as well switch. Besides like all the work and time and money and expense, but
Knowing what you know about the field, what would be your estimate, and I won't hold you to this, for the commercial lifetime of the RSA encryption algorithm?
Oh gosh. You're trying to make me say things, sir, that I'm not supposed to say. You're going to make me say my cheesy divine will joke again. I guess it's not quite divine will. Well, yes, this is divine will, but of the other kind, not of the Jensen Huang kind. I would say I've learned to never be surprised. That's my cop-out answer, but my honest answer. That some things have come along so much quicker than I ever thought. And some things they keep saying are like 5 years away, and 5 years keeps coming and going. I really couldn't put a time limit on it. I would say that a switch to post-quantum cryptography, I don't think it's bad. And my understanding, and I'm not a cybersecurity person, but my understanding is that's very powerful cryptography. So I don't think there's a lot of loss besides just the effort that goes into switching. But yeah, it's anybody's guess. The past 10 years here on Earth have been very surprising, and I expect them to continue to get surprising in every way.
There's something that you probably would have said on a different day, but if you have data at rest and it's encrypted with RSA and it has a lifetime of 5 years or more, then you're already at risk because somebody could go back and take that old data and decrypt it. So if it's state secrets or something like that, then it's already obsolete for that purpose.
Yeah.
In flight,
You never know. You never know, yeah. You never know. People never thought about the technologies that would exist one day, like genetic testing. That's gotten a lot of people into trouble. And, you never know about what you go back in time and unlock.
Another cybersecurity person that's like a cybersecurity group meet, but a second question off of what the gentleman said, and you probably give me a bad answer because it's a bad question, but he said, is there a time limit? And my question is more like, is it, in your estimation, an inevitability or not?
I would say all views are my own and do not represent those of NVIDIA Corporation. A very nice life, sir. I have 2 children. I have to feed them. No. I would honestly say that I don't know. I wouldn't, I'm not, I wouldn't gamble on it because I'm not supposed to gamble anymore. But I wouldn't gamble for it, and I wouldn't gamble against it. I really wouldn't put money on it. I wouldn't consider it a fair bet.
Hopefully getting back to something you can answer.
Thank you.
Because I'm not a cybersecurity person. The QEC decoding. My limited understanding, kind of the classical approach to error correction would be you just carry more redundant bits to do the error correction. And I think that's also kind of an approach in quantum computing is to carry more qubits for error decoding. Does the QEC decoding eliminate the need for redundant qubits or reduce the number that you need, or how does that play together?
That's an excellent question, and it really The answer is yes, you do need more qubits, but just like in classical error correction, where we don't just do the like repetition codes, we then move into like Hamming codes. Quantum has its own version of the Hamming codes. And they're multidimensional and they're strange, and you have to, it comes back to this measurement principle of you can't measure the wrong thing, you have to measure the right thing. And so they do require more qubits for sure, but just like the Hamming codes, they don't require just like straight up repetition. They require kind of a little bit of clever trickery and modular arithmetic kind of thing.
Okay, and the QEC decoding works with those sort of super Hamming codes, or?
It can, or it can do its own weird thing that's totally counterintuitive to us. Like there are codes that folks have come up with that are very based on that, and you could train a QEC decoder to just make the right predictions off of that. Or feasibly, you can have one that is predicting any old thing that makes random measurements or whatever. There's like a lot of interesting stuff right now too with like quantum low density parity check codes. And so that's coming online as well. We're not fully sure how to work with those yet, but it's anybody's ballgame right now.
Okay, thanks.
That's a great question though, and one I could answer. Thank you.
So Peter Shor was a one-man quantum algorithm genius, but there aren't that many Peter Shors. So, and we have Grover, but that's not even exponential. So let's say the hardware was here today. How close are we to actually being able to translate this into real advantage?
The algorithms issue is really tricky. You know that I can't even say as a physicist that we have Peter Shor because he's a mathematician. So anyways, but that's a grievance separate. But like the algorithms issue is actually really tricky. There's a lot of debates. So we would have a lot to do if you think that sub-exponential algorithms where we get a sub-exponential speed up will be good. So if you think that like a quadratic speed up will be helpful to us, then we're in good shape because we have a lot of stuff. We have like a lot of linear algebra things. We have some linear algebra things that are polynomial speed up. So okay, quadratic is 2, but some polynomial greater than the degree 2, right? I'm not aware of any linear algebra stuff. This would be like actually solving linear algebra using quantum computers. I'm not aware of any linear algebra things that have an exponential speed up. So it depends. There are theorists who argue like literally just this question about what degree of a quantum computer do I ever need to catch the overhead? What degree of a quantum computer do I ever need to make it worth it? If you're really strict about the exponential speed up, we don't have that many algorithms.
So your answer implies that these things might actually catch up to classical computing speeds, in which case you wouldn't need exponential speed up. But if they don't, then you pretty much would.
Yeah, a lot of people debate about, you know, what degree polynomial of speed up from your quantum algorithm would you need to make it worth it? And there's no general consensus on that yet.
But it sounds like they're more optimistic than I thought about these things actually getting to not horrible speeds.
There's a lot of smart people who are optimistic, for sure. And there's pessimists and there's everything under the sun. But yeah.
Cool.
Oh, thank you guys. Thank you. Yeah. Thank you.